الآن يمكنكم المشاركة في مبادرة الأيام الرقمية تحت شعار انطلق بقوة مع جوجل، والتي يتناول فيها خبراء جوجل عناوين جديدة أسبوعيا مثل السحابيات، مهارات من جوجل، أندرويد، فلتر، ذكاء الآلة، فايربيس، ديزاين ثينكينج، مقسمة إلى دورات وورشات عمل يومية بالإضافة إلى مسابقات أسبوعية. شاهد الأيام الرقمية مباشرة على اليوتيوب وشارك رأيك وأسئلتك مع خبراء جوجل، واحصل على شهادة حضور في كل محاضرة تشترك فيها. هذا وأكثر من الأحد إلى الخميس ابتداء من الساعة 9 بتوقيت دبي عبر الرابط المبين youtube.com/gdgmena.
Assalamu alaikum everyone. Hello to the session of MENA Digital Days. Thank you, MENA Digital Days and JDG MENA for inviting me to this session. And thank you everyone for attending this session. And I hope that by the end of this session, you will get to know and understand new things and learn new things about machine learning and reinforcement learning specifically. All the links and references I've used towards building the slides and this talk are in the second slide that I will be sharing with you by the end of this session. Today, we will see an introduction about reinforcement learning. In this talk, I will try to just explain the basics and the theoretical knowledge and foundation that you need to start using reinforcement learning in your work or in your solutions. This talk will be split into two parts. The first part is an introduction into reinforcement learning. And inshallah, in the next session, we will see a hands-on workshop on machine learning, on reinforcement learning, on some competitions and in Kaggle and Deep Racer problem by Amazon. I will be with you. I am Taha Bouhsine, a data scientist and a machine learning researcher and engineer from Agadir. I am the lead organizer of TensorFlow user group and the lead and founder of GDSA last year, and also the mentor of this year cohort of GDSA MENA. Today's talk, or the things that I really wish for you to take with you from this talk, is to learn the basics of reinforcement learning, as I said, and understand the difference between reinforcement learning and supervised or unsupervised machine learning, and where to apply these to, or when to apply reinforcement learning, and when to apply supervised or unsupervised machine learning, and also where to apply them, not just when, but where also to apply them, and the main concepts behind reinforcement learning agents and what differentiate between the different agents and the learning pattern of different reinforcement algorithms. And also, hopefully, you will get a first hands-on experience with reinforcement learning. I will follow this plan. I will start by an introduction into reinforcement learning. We will see what is RL, application of reinforcement learning, the tools that we use in reinforcement learning, and also a comparison between RL and supervised machine learning, and the key concepts and terminologies of reinforcement learning. We'll see the sales, observation, the policies, rewards and returns, and the RL problem that we are trying to solve, and where the value function comes in play. And also we will see the types of reinforcement learning and a small workshop that we will continue in next session, inshallah. And before we start with RL, and just like a thought play or a question that I had for a long time when I was growing up, and it was about how do we learn as humans, how we learners or any human, since we were babies, we found ourselves when we grow up, we talk in Darija for me, or in Arabic, just by nature. We didn't do any work, or we didn't do any, just read something that our parents gave us something to read to learn Darija. But we learn in a natural way that we were not conscious about it, and we were not thinking when we were trying to learn this not thinking, but we were not thinking explicitly to learn things like in the region. So now, how did we learn when we were babies? It was just like a question that I had, and I found the answer in reinforcement learning. And as you know, when we were kids, we did not know what is bad or what is good. We did not, when we were doing something, we did not know explicitly that thing, we should not be doing that thing, but we learned from that. We learned from our parents, we learned from our society, and also from our religion to just like stop doing the bad things and only do the good things. Or generally, we call that we learned from our environment that we grow up. So if we grow up in our country, like in Morocco, you will have a set of like a set of rules that you should follow to not to for the society to accept you. And same thing if you were if you did grow in Europe or in USA, you will have a set of different things and rules to follow for your country or for your people to accept you. And generally, we learn things by just like when we have a feedback from our society or from our parents. So when we do something great, our parents accept us and really cheer for us, and even give us a cookie or a reward for the things that we did, and we were really happy about it. So when we get a good grade in high school and in elementary school, so when we tell our parents that we did get a good grade, they will tell you good, and they will buy you a gift or something like that. And same thing, when we do something bad, we get our punishment. We get punished about it. So you have, I know you can get, you are feeling some goosebumps right now about all the flashback of things that happens in your home, and the things and the punishment that you get. But no worries, and we will move now to reinforcement learning, and we will try to like relate the things that are I just said about how the humans learn and link it with the reinforcement learning. So for reinforcement learning algorithms, it tries to just like gives the ability to agents that they call them agents, and give them the ability to learn by trial and error. You 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 put your agents in the environment that you are trying to learn from, that you are trying it to make actions on it, and give it the ability, give it the chance to make mistakes and learn from the trial and error. And whenever it did something good, you give it just like a reward. And also when it does something bad, or just like for this case, when it hit the wall, it dies, so you will give it a punishment of -1. And when it tries to jump, or when it learns to jump over the wall, you give it just like a reward for it to make it to like tahfiz, for it to repeat the same thing that it did last time, because it got more rewards, or just like forgo or forget the behavior in the future and not hit the wall again. And generally, these methods, or the reinforcement learning methods, are currently experiencing some great success, and specifically in the area of robotics and also game agents and self-driving cars and some stuff like that. For this example, we can train an agent to like learn how to drive a car and not quit the road and stay on the road as long as possible. And by doing that, if at first when it tries to drive the car, it will make some mistakes. It will drive out of the road. It might hit some civilians, and it might hit some just like some obstacles or some homes or some stuff like that, or other cars in the road. But with time, it learns how to drive and like not hit anything in the road. And also, you can train it to you can use it to train your robots to do backflips and cool stuff on even things that I can't do personally. And yeah, it tries at first. It makes mistakes, but as the time goes on, it makes a lot of it learns how to do those things better. And by the time you have you train it for a lot of time, you will have an agent that can perform that action without any problem. And it is also used for robotic surgery with Lean et al. I would share with you the article of the Archivix article by the end of this session. That helps the the surgeons perform surgery by using a robot, an accurate robot at that. And also it's used in games and building AI that can play games like the famous AlphaGo that beats the champion of the Go, and also sorry, and also the Dota AI that was developed later years in to play against and beating the champions of Dota that year. And also it tries to simulate the robots to follow the human instructions in general. And also it was used to train the Atari and to play the Atari. And lately it was used, these reinforcement learning algorithms were used to just help a robot perform a task that was given to it by a simple text. It was not just it tries to understand the problem and try to plan a set of actions to solve that problem. For this example, and the human types that he spilled some Coke on the bin, and he asked the robot to just hold the cup and put it into the trash bin, and then try to find something to wipe the Coke that he spilled. And he didn't ask it to perform this one step at a time, but he gave it a full text to perform it. And yes, it takes a lot of time because this technology is just begun, because they speed up this video by by 10x. And sorry, they speed up this video by 10x, and the robot takes a lot of time to just understand what he is supposed to do and then perform it. And they train these robots using reinforcement learning and some language models. To train those models, there are a lot of libraries and frameworks that can be used, like Quarks, which is built by Microsoft based on JAX, and RLX that's built by Google DeepMind, and TensorFlow agents that can be used also for this type of problems or reinforcement learning problems. You can train your agents. You can train them on a set of environments that give you the ability to just perform an action in a simulated world. In a simulated world that is not risk-free and you can't hurt anyone in it. I will be talking about environments later. And also Open AI Gym that give you the ability to use the predefined environments, and also you can create a container to your personalized or customized environments, and then use it to train your agents. And you might ask that how is this reinforcement learning different from supervised or unsupervised machine learning? Are they the same thing, or is everyone have a specific use case? Well, generally, for supervised and unsupervised machine learning, you have a data set or a set of data points, and you try to just like for each of those data points, find a label or find a decision to make. And each of those decisions or each of those data points are not related in any way. And for example, if this is a cat, it doesn't mean that the image that follows it has to be a dog, but it's a set of things that are separate. Or unlike in reinforcement learning, it is a dynamic. Sorry, there is a typo there. It is a dynamic. It is used for dynamic things. So, if an action, if your agent take an action right now, it surely will affect all the actions that he would take afterwards, and there is no explicit right answer. So, the agent doesn't know that the next action is the right one, but he tries to make those decisions based on a set of experience that I had, and he's trying to like optimize the final result, and not the current result, but the final result of the whole experiment in the training of it, of course. And like the supervised or unsupervised, each of those data points have a single true value. It's not just like not defined. But for reinforcement learning, and it has a multiple decision process that can, each of those decisions that he make along the way affect each other and affect the results, the end results of the reward that will be given to the reinforcement learning agent. And for supervised and unsupervised machine learning, each of those data points have a single value, and so one decision at a time, not multiple decisions. And you cannot, for this reinforcement learning, and like supervised and unsupervised, you can just like use training data that you have validated and have collected, and then train your models on it. But for reinforcement learning, it has to experiment. It needs to experiment the policy or the thinking process but the thinking process that it has on real world to improve it, and to learn from the experiment that it does. So you have to put it into an environment and make it learn by doing mistakes. And by doing mistakes, you cannot put this machine learning or this reinforcement learning agent into real world. You cannot put a self-driving car and you just started training it, and you have to put it on the highway to, okay, go train and come back when you are ready. You cannot expect it to come back, because it will just like hit something in the road or something, or might hurt people. So it's quite expensive to really train it if you didn't have train it on in the real world. But you can train it in simulated environments. This is the age of simulation, and everything, all the environments that you can think of can be found. You can build a simulation of. For example, if you want to train a car, you can use Unity or something like that to like have a steering wheel and acceleration and brakes, and give it to a car or to your reinforcement agent, and he will learn how to use those the steering wheel and the brakes to really learn to drive. And it is a risk-free environment. Even if it hits a wall or something in the simulation, it's okay, because it's just a simulation, and like in the real world. And you cannot, it's not totally separate from machine learning from supervised or unsupervised, because you can use also the things that you learned, or the methods of machine learning, like gradient descent, and use it into reinforcement learning. They are different, but they are parallel. It's not totally different, but they have just like some small differences between them. And yeah, it requires you a simulated environment, and it has a sequential decision-making scenarios. And to do that, And to do that, you can use the for this reinforcement learning agent to train. It needs an environment, and so by observing these environments, um, the interpreter, just like the interpreter, tries to observe, take that observed environment and use the state to feed it to the agent, for that agent to take an action that will affect the environment. And the interpreter will try to observe the environment again, and then decides whether to reward or punish the agent. And uh, it's not just like if an agent did something right now, he might be punished just like a small punishment. But when the next time or the next action is that it's the time for the next action to occur, the agents might find a better action to take based on the bad action that he took before. So it's not just like this decision is the right one, but it's a set of decisions that really makes the agents have this like a trajectory to follow, and not only just like uh, based on only once a single action. For the environments, it's just like if we want to build a chess AI that an AI that can play chess, the environments is the chess board. And if it's a robot, like for example, a robot that can do the stuff that can do laundry and stuff like that, it is the room, the actual room of it. And if it is the chatbot, it is the chat app that you are trying to build a chatbot for. And a vehicle, it is the road or the simulated road. And if it is a program like a time series or a financial program that can predict the stock market prices and decide whether to buy or sell, it is the data. Or if it is a machine that will try to like collect tomatoes or potatoes from the field, it is the working field of that machine. And to define, and what we can, as we said here, it's the interpreter tried to observe the environment and then use that state of the environment. So we need a state, or we need an observation of that of the total state of the to feed it to our agent, the yellow arrow at the bottom. So we need the state to give it to the agent. So the state is usually denoted for mathematical purposes. It is usually denoted as S. For example, it is the whole state of the board, just like each of those the board pieces. When you give the agent the whole state of the board, or the whole system state, if you have just like a farm or something, you give it all the information about the state of the farm, and then make it try to act in it. Or if you are using just like a partial state or a partial observation of that state we just talked about, you call it an observation, which is just like a video. For example, the video that you capture it from the camera of the robot, or just like what can the robot see in front of him, not the whole scene or the whole farm and the whole data that you have collected on the farm, but it's just like what can the robot see. So just like if he tries to collect the tomatoes, he can just like know the existence of the tomatoes in front of him, and not just like the whole farm or the whole where he can find the tomatoes in the whole farm. And also you can just like when you give the just like the position, his actual position, a GPS location or something, and the inner state of the robot's components, just like what he is doing right now, that's called an observation. So the state is the complete description of the state of the world, and the observation is like a partial state that can or partially observed from the environment. And then there is the agent that is the one that will have to make the decision at the end. So when you give him a state, he have to think, or he has to decide which states, which decision to, or which action to make from the actions that I can make. How should I act? And given a state, of course, given a state, how can I act from the action that I can make? And the actions that he can make are defined in by the environments. Just like if you give him a controller, he will have only the buttons on the controller to make those actions. So the action space is the set of actions that the agents can make. Like if you are trying to play to make an agent that can play XO the game, you can, or the 3x3 XO, you can just like those. The action space is the 9x9 grid, and the position that he can put his X in which cell he can put the X in. So the different environments allow different kinds of actions, and the sets of all valid actions is given by an environment, and it's called often the action space. And like in the Go, there is like I think 23x23 grid, and in chess there is also the grid where you can put the chess, and each of those chess pieces, what are the actions that you can, where you can move them and stuff like that. And based on those actions and based on the action space, the agents have to learn a policy, the policy that can help him decide which action to take. For example, if there is a chessboard, and you know that the chessboard, we have a deterministic, or we have a value, a set of choices that we can count by hand, and which is called deterministic. And you can note it like the me of state of t. The state is s, as we said earlier, of the state that we have. And so the action at the time t as the me action, the me of the state of c. So it's the policy me of the state of c. And the action, if we have a stochastic or a stochastic action, like how should he move his hand or his body or his robot? It's not just like 1 and 2, 3, 4, but just like a continuous number. So we can denote it by pi, pi of dots slash state of the t. And because this policy is essentially the brain, the agent's brain, it's not just like we can call sometimes you find some in the literature, you can find them calling it policy or agents, but it's just like the policy is trying to maximize reward, if by example, which is the agent is trying, it's the same, it sounds the same like the agent is trying to maximize the reward. And yeah, based on the set of actions that were this policy, the agent has the ability to just like build this trajectory, or T or TO, which is a sequence of states and actions in the world. And generally, but in the first one, the state 0, it's just like a randomly sampled state that helps the model, that gets the model to stop. And then there is the reward and the return, as we said earlier here. The interpreter, after the interpreter, the environment feed the interpreter the observation. The observation is fed then to the agent to just like use that state to take an action that affects the environment, and then it will observe the environment and give a punishment or a reward to the agent. So the reward is just like a function, and that it's critically important in reinforcements. And it depends on the current state of the world that will just fed the agents, and the action just taken before. And based on those two actions. And we need also to know the state of the model at the next step to calculate the reward, whether our agent did a good job or not. And based on that, we give the agents a reward, or we should give him the punishments. And so the main problem of the reinforcement learning, and whatever the choice of the return measure, and whatever the choice of the policy or all those things, its goal is to select the policy which maximizes the expected return when the agents try to act according to it, just like based on a set of actions. It tries to the reinforcement learning tries to look for the best policy that gives it the best results or the best reward in the experiments, in all experiments that it does. And to use that, they use the value functions, and those value functions differ from there are different types of value function. There is the on policy, the on policy value function, which gives the expected return. If you started in a certain state, and it uses the policy, it only uses the policy. And also there is the on policy action value function that gives also the expected return if you start in a state and take an arbitrary action, and then forever after according to then also acts according to the policy. Then there is the optimal function, and there is the optimal action value function. We will try to look at these policies in the next session more and get our hands more into them, just like build some reinforcement agents using different type, and we will focus more on the Q-learning, inshallah, in the next sessions, inshallah. So, what are the types of reinforcement learning algorithms? There are generally two types. There are the model-free and the model-based algorithms, and we can decide which one we should learn based on a set of questions. Whether when on this question, when we are trying to decide what are we trying to learn, are we trying to learn the policy, just like the brain of we are trying to learn the brain of the agent, or we are trying to maximize the action value functions or the value functions, or we are trying to just like make the model learn from the environment and learn the model of the environment and understand the environment more. But for this last type, it might create a biased model that will only learn how to act in that exact environment and not perform good as other environments. For methods or for model-free methods, there are generally two types of model-free methods that doesn't require you to learn from the environments, but it will help you just like learn a set of policies or a set of things that will help your model make better actions. And for the first one, the policy optimization, it represents a policy that is that tries to that we generally just optimize it with using gradient descent, same as other types of supervised and unsupervised machine learning. And it does that by just like maximizing the local approximation of the loss function, also just like similar to the supervised machine learning. And also there is the other one, which is the Q learning. We will be looking into it more into the next talk, and we will try to get our hands, as I said, our hands dirty with it, using both TensorFlow and Flux, inshallah. And then there is the other one, which is the model-based, and there is the background pure planning, which just like understand what happens into the whole state of the environments, and it tries to make actions based on that. There's also the expert iteration, which is a straightforward follow-on to the the pure planning, like planning the whole stuff based on a set of actions. But we will be more focusing on the model free in the next session, inshallah. And this is the general taxonomy of all the machine learning or all the reinforcement learning algorithms, and you can find it in the link, in the second link in the reference in this talk, inshallah. And it is just like to help you with whether to decide on building a model free or a model based, because just answering this question will really help you build better. You might just like understand how to select which model will work for you better, because each problem has you find that each of those algorithms is better be used into a set of specific problems, and wouldn't work at all if you or can fail or can either fail in production if or have a set of a lot of bias into that environment if you use it. So we will be talking about it later in the next talk, inshallah. So in the next talk, we will try to, inshallah, build some agents and use them for the competition available on Kaggle, which is ConnectX competition, and just like an introductory competition. And then we will see, if we have time, we will see the Deep Racer competition by Amazon, and we will look more into policy optimization or Q-learning and build some great stuff, inshallah. Do you have any question? Okay. There is what are the reinforcement learning algorithms that most used in the video games industry? Thank you. Regard. For the second question, how to train the reinforcement learning algorithms and what are the simulation environments to do it, how to proceed to deploy the IDE. For the first one, how to train the reinforcement learning algorithms, it's similar to how we train the machine learning algorithms. It tries to just like use the gradient descent to train the policies or the brain of the reinforcement learning agents and help it just like from trial and error. We will see more practical example in the next session, inshallah. And also for what are the simulation environments to do it. I've talked about Brax and also about OpenGem AI. Or also there is, if you are interested in training it for games, there is also the Unity machine learning, the Unity machine learning agents library. You can use it to train your game agents into it. I don't know what kind of games. If you are talking about 3D games, you can use Unity to train them. If you are trying to build like board games or something like that, there is also the OpenAI gem that I talked about here. Just like, I think, yes, I talked about it just here. Yes, no. That provide you with a lot of, yes, I will share with you this presentation, which the presentation that was just like shared by the facilitator. Thank you. The presentation, and you can, there is all sorts of stuff there, and I will be sharing more information about this reinforcement learning and in my blog if you are interested. I think it's not, here's the blog. You can find more. I will be posting it in the future, inshallah. Just enter this presentation that I just shared with you, that the facilitator shared with you. Okay, you need access. Okay, sorry. I will share it with you just right now. Hold up. Okay, I will share it with you. I will change the accessibility to the doc just right after the talk, inshallah. Just keep the link to our projects. Okay, depository. Okay, tree. In a project depository tree. I did not understand your question. You can contact me in my email, and I will try to understand what are the projects that you are currently working on. Here's my email. You can find it in the last slide. Okay, just let me share it with you. You can contact me in my email, and I will try to continue the discussion with you, inshallah. If you have any other question, we will get to understand these things better in the next session, and we will get our hands dirty with the presentation. And thank you very much, everyone, for attending this session. And I hope that you learned something new. And until the next session, I will have to leave you here. And thank you very much, JDG, MENA, for having me again. And thank you for the hospitality. And have a great day, everyone.